Good evening, and welcome to Quiet Science. Tonight, we're going to slowly explore a question that begins at the edge of the shore. What decides where a wave will break? We'll move gently through the hidden balance between wave height, wavelength, seabed slope, and water depth, one idea at a time, with plenty of space to breathe between each one. Some of what we discover tonight will feel familiar. The hush of foam, the curl of a crest, the steady pull of water across sand. But beneath that familiar motion is a quiet pattern, shaped by tides, sandbars, gravity, and time. If you'd like to join us for more nights like this one, you're welcome to like and subscribe below. It means the world to this little channel. But for now, all you need to do is get comfortable. Let your breathing slow. Let the shoreline do the rest. Let's begin. A wave does not wait for the shoreline to begin changing. Its transformation starts farther out, in the place where water depth becomes small compared with wavelength, the distance from one crest to the next. There, the moving form begins to feel the seabed beneath it. The contact is indirect and gradual at first, but it matters. A long wavelength swell can interact with the bottom in deeper water than a short, choppy wave, and so its alteration often begins farther offshore, long before the final line of surf is formed. Wave period, the time between crests, helps determine wavelength and speed, and in that quiet way it helps decide how and where shoaling begins. Before any crest breaks, height already has a role. A taller wave carries a steeper face from the beginning and needs less additional steepening to become unstable. The ratio between wave height and local water depth is one of the simplest clues to what is coming, because a wave cannot grow steeper without limit in shallow water. Even before the final collapse, the balance is being set between the shape of the wave and the shape of the bottom below it. Storm swell commonly arrives with greater height and longer period than local wind chop, and so it reaches the coast with a different starting balance between steepness, depth, and bottom slope. In sheltered bays, smaller waves may never reach the steepness needed for dramatic plunging, even where the beach itself is relatively steep. The seabed has its own patient influence. Its slope determines how quickly depth decreases toward shore, and that rate strongly affects whether a wave gives up its energy gently or all at once. A gently sloping sandy beach usually offers more distance for adjustment. A steep beach compresses the same adjustment into a shorter run-up zone. Coarse pebbles often help a beach remain steeper than fine sand does, so sediment size indirectly shapes the kinds of breakers that are likely to form there. The beach face, then, is part of the decision. Depth is never fixed by profile alone. Tide level shifts the water depth at the moment a wave arrives, moving the breaker location landward or seaward. A bar that lies just beneath the surface at one stage of tide may sit under deeper water at another. Offshore sandbars act like underwater steps, creating shallower patches that can trigger early breaking before a wave ever reaches the visible shoreline. Near river mouths or barrier inlets, channels and shoals change with time, sometimes from week to week, rearranging depth patterns and altering where familiar lines of surf begin to topple. The approach of the wave matters too. Waves that come straight onto shore often break in more even lines. When they arrive at an angle, some sections meet changing depth sooner than others. The bottom is encountered unevenly, and the line of breaking can begin to vary along its length. Natural seas are irregular as well. They do not send identical crests one after another. They arrive in groups of larger and smaller waves, each crest carrying slightly different starting conditions even along the same beach. One line may pass with little consequence. The next may meet the same slope and depth with a different height, a different wavelength, a different balance, and break in another way. So the place where a wave will break is not marked by a single boundary drawn across the seafloor. It is set by several conditions meeting at once: height, wavelength, period, local depth, the slope of the bottom, the shape of bars and shoals, the stage of the tide, and the angle of approach. All of them work together before any white water appears. The sea seems to hold the answer in motion long before the crest yields it. As a wave enters shallower water, the change begins in its lower part. Interaction with the seabed slows the motion below, while the upper part continues moving faster for a time. The wave is still one form, but not every part of it is advancing equally. Uneven slowing creates a subtle distortion. The base is checked by the bottom, while the upper water keeps more of its pace. From this small difference, the larger transformation unfolds. The wave is no longer simply traveling through open depth. It is being reshaped from beneath. As that interaction continues, wavelength shortens. The crests crowd closer together as the wave approaches shore. The distance from one crest to the next decreases because the waveform is being compressed horizontally while still carrying its energy forward. A broad spacing that belonged to deeper water narrows in the shallows. The pattern tightens. This shortening is one of the quiet signs that the bottom has begun to govern the wave more strongly. The sea surface does not merely rise and fall in place. Its geometry changes as depth declines. With less horizontal distance available, the energy of the wave is squeezed into a shorter span, and the crest often grows higher. This is shoaling. The wave gathers upward as it is compressed forward. Height increases because the existing motion is being concentrated into a smaller horizontal length. The seafloor, by changing the speed and spacing of the wave, lifts the crest toward a new form. The wave becomes more prominent, more elevated above the surrounding surface, even before it begins to fail. Shoaling does not stop at simple growth in height. As it continues, the front face of the wave becomes steeper. The crest rises while the lower part is increasingly slowed, and the forward face leans more sharply. There comes a point when gravity can no longer keep the crest smoothly supported. The shape has become too steep to remain a stable traveling form. The wave has been carried toward instability by the same process that raised it. The steepening is gradual, but the threshold it approaches is definite. Breaking begins when the crest outruns the waveform beneath it. The top starts to spill or pitch forward because the support below no longer keeps pace with the motion above. The wave does not simply stop being a wave in one instant. It begins to transform. The crest moves ahead of the body that had carried it, and the ordered shape gives way to collapse. At that moment, the difference between spilling, plunging, and surging begins to declare itself through the way the crest yields. On a gentle seabed slope, depth decreases gradually, and the wave has more time to adjust as it shoals. Because the change is spread over a longer shoreward distance, the wave usually breaks in a spilling style. The crest does not gather into a single heavy lip. Instead, it gives way more continuously. The bottom has not forced a sudden steepening. It has allowed a long approach toward instability, and the release follows that same gentler pattern. A broad, patient slope tends to produce a broad, patient break. In a spilling breaker, the crest topples in small increments. A tumbling white edge forms and renews itself as the wave continues shoreward. The collapse is not concentrated into one compact throw. It is repeated along the upper front of the wave, moment after moment, as if instability is continually being reached and released. The white line advances with the wave, and the breaking remains active over a longer zone. The form is still moving shoreward, but its crest is being steadily spent. That white water exists because falling water traps and shreds air into countless bubbles. The smooth surface is replaced by a froth of water and air mixed together in rapid disorder. The bubbles brighten the break zone and give spilling surf its long, foamy character. This is part of the physical transformation of the wave's energy into turbulence and aerated water. The crest falls, air is caught and torn apart, and the wave becomes a moving band of foam. On a steeper seabed, the process is compressed. Depth decreases more quickly, and the wave is forced to steepen rapidly. The crest can gather into a single thicker lip rather than toppling away in small repeated pieces. The wave has less distance in which to adjust, and so the instability arrives more abruptly. The bottom does not gradually persuade the crest to give way. It drives the shape toward a sharper failure. Under those conditions, plunging becomes more likely. In a plunging breaker, that thicker lip curls over and throws forward and down. For a brief moment, it encloses a pocket of air before collapsing. The wave face becomes a curved wall, and the crest leaves it as a distinct mass. This is a more concentrated kind of breaking than spilling. The crest gathers, pitches out, and falls. The air pocket exists only briefly, held between the curling lip and the face beneath, and then it is crushed as the falling water lands. When the lip lands, turbulence is sent downward and outward. Water, air, and suspended sand are mixed together in a compact burst. The collapse is forceful because so much of the wave's energy has been concentrated into a short distance and a short time. The ordered motion of the crest becomes chaotic, swirling water. Sand that had rested or drifted near the bottom is pulled into the mixture. The break zone thickens with bubbles and suspended grains as the plunge completes itself. There are shorelines where the crest does not fully curl at all. If the beach face is very steep and the nearshore water remains relatively deep until the last moment, a wave may surge up the shore without forming a fully plunging lip. In that case, the collapse is delayed. The wave keeps much of its shape until it reaches the beach face itself, where it runs upward in a strong rush. The difference lies in timing. The instability is not released offshore in a broad white tumble or a forward-thrown plunge. It is carried almost to the shore. A surging breaker, therefore, shows less offshore tumbling foam. Much of the collapse is postponed until the water is already rushing directly onto the beach face. The break zone is narrower, and the wave's momentum is spent over the steep shore itself rather than in a wider surf band. The water gathers and runs, with less of the prolonged white cresting that marks spilling and less of the thrown lip that marks plunging. The motion is still a breaking wave, but its energy is expressed in a different place and in a different form. Wave period quietly returns here as an influence. Longer period waves often build a thicker, more organized crest before breaking, and when the bottom slope is suitable, that can favor plunging. The wave has a structure that holds together farther into shoaling, allowing the crest to gather before it fails. The outcome still depends on depth and slope, but period helps set the wave's manner of arrival. It contributes to whether the crest remains coherent enough to curl as a single lip. Shorter, steeper wind waves often behave differently. They tend to lose their shape more quickly, and this often leads to messier spilling rather than a clean plunge. Their form is less organized as they shoal. The crest begins to give way in a more fragmented manner, and the break becomes less like a thrown curtain of water and more like a repeated tumbling edge. The same shore can therefore receive quite different breaker styles from different kinds of incoming seas. simply because the waves bring different starting shapes and periods with them. Within the shoaling crest, the water particles near the top move in tighter, more forward-leaning paths. That motion adds to the instability of the upper part of the wave. The crest is higher and steeper, and its internal movement is becoming more inclined toward forward collapse. The geometry of the wave and the motion within it begin to agree on the same outcome. The top is being prepared to outrun the form beneath. The final failure is visible at the surface, but it has already been organized by motion within the wave itself. The point of first breaking often appears where local depth reaches a critical fraction of wave height, though the exact fraction varies with wave shape and slope. This is why height relative to depth offers such a useful clue. A wave cannot continue steepening indefinitely as the bottom rises beneath it. Yet no single fraction gives every answer, because shape and slope modify the threshold. A taller wave in the same depth generally nears instability sooner, while a different bottom profile can delay or hasten the moment. The critical point is simple in principle and variable in detail. Offshore bars complicate the path in a quiet but important way. A wave crossing a bar may begin spilling there, then reform in slightly deeper water behind the bar, and break again closer to shore. The seafloor creates more than one opportunity for instability. The first shallow patch trips the crest. The deeper trough behind the bar allows some recovery of form. Then the inner slope toward shore brings the wave once more toward breaking. A single incoming crest can therefore pass through several stages, each shaped by the changing depth beneath it. When waves approach at an angle, one part of the crest can enter shallow water before the rest. Then the line of breaking does not collapse everywhere at once. It peels along shore. The shallower section slows and steepens first, and the breaking point travels along the crest as neighboring sections meet similar depth. The result is a line that seems to release itself progressively rather than simultaneously. Angle of approach turns depth into a sequence along the crest, not only across it. This uneven slowing along the crest is part of refraction, the bending of wave crests as different sections slow by different amounts. Refraction begins before the break itself. Where one section of a wave encounters shallower water and slows more than another, the crest changes direction and shape. The bending helps determine where energy gathers and where it spreads. The wave is not merely moving toward shore over a fixed bottom. It is being redirected by variations in depth beneath different parts of its own length. Where refraction focuses energy onto a headland or the crest of a bar, waves can become steeper sooner and break more forcefully than nearby waves. The same incoming swell does not meet every part of the coast in the same way. Bending can draw more energy into one section, increasing the height and steepness there relative to surrounding water. A favored zone emerges, and the break becomes earlier or stronger in that place. The bottom shape below and around the wave helps gather the conditions for a more forceful collapse. Where refraction spreads energy across a wider front, the opposite tendency appears. The same incoming swell may break more gently and farther inshore. Energy is distributed over a broader span rather than concentrated into one favored line. The crest still shoals, still steepens, still approaches instability, but it does so with less intensity in any one place. Refraction does not only bend waves, it prepares different sections of coast for different styles and locations of breaking even under the same offshore swell. During breaking, part of the wave's energy becomes turbulence, the chaotic swirling motion that rapidly mixes water and bubbles. The ordered travel of the wave is converted into a dense, restless agitation. The collapse does not simply erase the wave. It redistributes its energy into smaller, irregular motions. Turbulence fills the break zone, carrying bubbles downward, lifting sand, and stirring the water into a temporary clouded mixture. In that state, the wave's former shape is gone, but its energy remains active in another form. Some of the energy also becomes sound. This is why a plunging collapse can produce a deeper thud than the softer hiss of spilling surf. The style of breaking shapes the coast's soundscape because it shapes how and where water falls, how abruptly air is compressed and released, and how concentrated the collapse becomes. A long, tumbling edge of spilling foam stretches its release over time. A plunging lip gathers it and lets it go more suddenly. The difference in form becomes a difference in sound. In the aerated water of the break zone, bubbles make the water less dense for a moment. That brief change affects how sand grains and foam are carried. Suspended material moves through a mixture that is not quite like clear water. The bubbles alter buoyancy and the texture of the flow, helping determine where grains settle and where they remain in motion. The break zone is therefore a place of surface collapse, and a zone where the physical character of the water itself is briefly changed by air. Immediately after the collapse, the uprush called swash begins. Water and sediment are carried up the beach with momentum inherited from the breaking wave. The crest has fallen, the turbulence has spread, and then the water gathers into shoreward motion along the beach face. Sand and pebbles can be moved with it, depending on the shore. The swash is the continuation of the same event in another form. Breaking does not end at the moment of collapse. It runs on as shoreward rush. The returning backwash then meets the next incoming wave, and that meeting can soften or sharpen the next break depending on timing. The beach face is therefore not reset to stillness between one crest and the next. Outflow from the previous wave remains active. If the returning water meets the incoming wave in one phase, the new crest may be altered before it breaks. If it meets in another, steepness can be enhanced. The breaking pattern is linked from wave to wave by this exchange between retreating and arriving water. On barred beaches, the trough between bar and shore can momentarily deepen the water enough to delay a second break until the crest reaches the inner slope. After a wave has broken on the bar, the deeper trough offers a short reprieve. The crest, or what remains of it, travels through greater depth, regains some shape, and then meets the rising bottom again nearer shore. The placement of bar and trough therefore controls not only whether there are two breaks, but where the inner one happens. Tide changes this arrangement even when the bar itself does not move. As tide rises over a fixed sandbar, the same wave may stop plunging on the bar crest and begin spilling farther shoreward instead. Greater depth over the bar reduces the abruptness of the interaction there. The first break weakens or shifts. The wave carries more of its form landward before it yields. A single shore can therefore present different breaker styles over the course of a tide without any change in the incoming swell itself. As tide falls, reduced depth over bars and shoals can make waves trip earlier, shifting the active break zone seaward. The shallower crest of the bar reaches the critical depth-height balance sooner, and breaking begins farther from shore. What was a later or gentler break at higher tide can become an earlier and more abrupt one at lower tide. The moving water level redraws the effective shape of the seabed from the wave's point of view. The steepness of the incoming wave also matters in a direct way. A steeper wave, meaning one with larger height relative to its wavelength, generally reaches instability faster than a flatter wave in the same depth. It begins closer to the threshold even before shoaling intensifies it. When the bottom starts to slow the lower part and shorten the wavelength, less additional change is needed before the crest outruns the form beneath. Steepness is therefore part of the wave's starting condition, as well as an outcome of shoaling. Because natural seas arrive in groups, this balance can shift from one crest to the next. Even within a single wave group, a larger set wave can plunge where the smaller waves before it only spilled, simply because its greater height changes the balance. The beach has not changed in that brief interval. The tide may be nearly the same. The bar may lie in the same place. Yet the larger crest arrives already closer to instability, and the style of breaking changes. The coast receives not one repeated event, but a sequence of related variations. Breaking itself is not a single instant. It is a short transformation zone where crest collapse, bubble formation, turbulence, and shoreward rush overlap. The waveform passes through stages that merge into one another. The crest begins to fail, white water forms, air is trapped and shredded, turbulence spreads, and the broken water continues shoreward. Even the categories of spilling, plunging, and surging are names for dominant tendencies within this moving interval, not separate isolated moments. In the very shallow final stages, the broken wave becomes a bore, a low wall of foamy water that continues shoreward after the original crest has collapsed. The organized crest is gone, but a new form persists, a shoreward moving ridge of broken aerated water. The bore carries the last broad momentum of the event across the shallows. It belongs to the wave's afterlife, if the word is allowed, the continuation of movement after the original shape has already been spent. And so the type of breaker is not decided by one number alone. It comes from the combined timing of wave height, wavelength, slope, and depth. Period helps determine wavelength and speed. Tide shifts local depth. Bars and shoals interrupt the path. Angle of approach and refraction alter how different sections of the crest meet the bottom. The wave's own height and steepness prepare it for one threshold or another. The final style of breaking emerges from all of these conditions meeting in time. When a breaker spills, its energy is usually released gradually across a broad surf zone. The shoreline is met by a long, foamy push rather than one sharp impact. The collapse renews itself over distance, and the water arrives already thick with bubbles and turbulence that have been spread out along the approach. The result is a broad band of active water where the wave's force is distributed rather than concentrated. The sea gives itself to the shore in a prolonged way. A plunging breaker behaves differently. Its force is concentrated into a short distance, and that focused impact can dig a steeper beach face or deepen a trough just offshore. Because the lip throws forward and lands compactly, the bottom receives a more abrupt burst of turbulence and motion in one preferred zone. Repeated plunging there can carve offshore bars and troughs, and those features then modify later waves, influencing where the next lines of surf will break. The breaker helps shape the bottom that will shape the next breaker. Surging breakers spend more of their momentum on the beach face itself, often with little foam. Their narrower breaking zone means less energy is lost offshore in a tumbling collapse. On reflective, steep beaches where surging breakers are common, swash and backwash can move pebbles and coarse sand back and forth with little time spent suspended. The grains are shifted by repeated rush and return along the steep face, rather than held for long in broad aerated surf. Because breaker type changes how sand is stirred, the same coast can alternate between flattening and steepening as wave conditions shift through seasons or storms. Gentler spilling surf tends to keep more suspended sand moving along the shore, helping longshore drift quietly redistribute beach sediment from one stretch to another. A different season or a different kind of swell changes the balance of height, wavelength, slope, and depth, and the beach begins to reshape itself in response. The coast is not fixed between one pattern and the next. It adjusts under the repeated decisions of breaking waves. Breaker patterns also help shape habitats. Broad, foamy surf can oxygenate shallow water and shift fine sediment differently from a narrow, forceful plunge zone. The width of the surf band, the amount of aeration, the way turbulence spreads or concentrates, all of these influence the shallow margin where water and sediment remain in motion. A coast of long hissing spill has a different nearshore rhythm from a coast of short heavy plunges or steep surges. The forms of breaking become forms of environment. Even the sound of a coast carries this distinction. Spilling surf produces long hissing foam. Plunging surf creates shorter, heavier crashes and booms. Surging breakers often rush with less offshore tumbling. Each style gives the shoreline a different pattern of release because each style converts wave energy into turbulence, foam, and collapse in its own way. The sound is not separate from the physics. It is one of the ways the breaking pattern continues into the air above the water. Broad prediction is possible from wave and beach measurements. The combined conditions of height, wavelength, slope, and depth give strong clues to whether a wave will spill, plunge, or surge. Yet exact breaking points still vary with shifting sandbars, tides, and irregular wave groups. A familiar coast can hold its tendencies and still change from day to day, tide to tide, crest to crest. The answer is never carried by the wave alone or by the beach alone. It belongs to their meeting. That meeting remains delicate even when it is forceful. A long period swell begins to feel the bottom in deeper water. Its wavelength shortens. Its energy is squeezed upward into shoaling height. The front face steepens. The crest leans beyond support and spills, or curls, or runs upward almost unbroken until the last moment. Beneath that visible change lie the quiet controls of slope, depth, tide, bars, and approach. The breaking point is not a fixed line, but a moving agreement between shape above and shape below. Along one shore, the same incoming sea may begin spilling on an offshore bar, reform in a trough, and plunge on the inner slope. Along another, a steep reflective beach may turn similar energy into surging uprush with little offshore foam. A larger wave in a set may plunge where the smaller ones only spilled. A rising tide may shift the active break landward. A falling tide may trip it early over a shoal. The coast keeps revising the answer because the conditions that decide it are always in motion. What decides where a wave will break, then, is not a single threshold standing alone in the water. It is the timing of several thresholds at once. Height relative to depth, wavelength shortened by shoaling, steepness increased by compression, bottom slope determining whether change unfolds gently or abruptly, refraction focusing or spreading energy before the crest has even begun to fail. Each factor waits within the others. The final white line is only the moment when all of them become visible together. And after that moment, the water keeps going. Foam drifts shoreward in a bore. Swash rises and backwash returns. Sand is lifted, dropped, drawn along, or carried back. Bars and troughs are adjusted little by little, preparing a different bottom for later waves. The coast is shaped by the manner of breaking, and the manner of breaking is shaped by the coast. In that slow exchange, every crest arrives with a question already partly answered by the ones before it. So the sea settles into a continuing conversation with the shore, spoken through depth and slope, through height and period, through the brief leaning of a crest that can no longer hold. Some waves release themselves in a long, foamy spilling. Some gather into a heavy plunge. Some rush steeply upward in surge. Each form begins offshore, where wavelength first meets shallowing water, and each comes to rest only after collapse has become swash, and swash has become return. The decision is made in motion and remade with every arriving line. Far offshore, a line of swell moves in the dim water. Its crests are spaced far apart. Its shape seems patient. Beneath it, the seabed is still distant, and then, little by little, not so distant anymore. A wave begins to feel the bottom when the depth grows small beside its wavelength, that quiet distance from one crest to the next. The longer swell feels this sooner. It starts to change farther from shore, in places where short, choppy waves might still pass almost untouched. Nothing abrupt is needed at first. The lower part of the wave meets resistance below, while the upper part keeps on for a little while in its old way. The change begins underneath. It is hidden there. Above, the crest still looks calm, yet the water is already entering a different arrangement, one that draws the crests closer together as they come in. The spaces shorten. The lines crowd softly. A taller wave arrives with more steepness already in it. A longer period swell carries a broader, more organized shape. A smaller local chop comes in differently, quicker and rougher, more easily loosened. And under all of them, the shore waits with its own quiet geometry. A gentle sandy slope with room for adjustment, or a steeper beach that asks for everything in less distance. Tide shifts this meeting place. a little more water, and the break moves landward. A little less, and it starts farther out. An offshore bar can lift the bottom like a hidden step. A familiar line of surf can rise there first, before the visible shore is reached at all. Sometimes the incoming lines are even and nearly straight. Sometimes they arrive at an angle, and one part touches shallower water before another. Then the break does not happen all at once. It begins in one place and travels along the crest. Even in quiet repetition, no two arrivals are perfectly the same. Natural seas come in groups, larger and smaller together. One crest follows another with a slightly altered balance of height and depth and slope. The shore receives each one separately. As the water shallows, the wave gathers itself. Its lower part slows against the seabed. Its upper part still carries forward. The crest rises because the same energy is pressed into a shorter reach. The face grows steeper. The front leans. There comes a moment when gravity no longer keeps the top smoothly held in place, and the crest begins to outrun the form beneath it. Then the wave gives way. On a gentle slope, this giving way is often gradual. The crest topples in small pieces. A thin white edge forms and forms again, renewing itself as the wave continues shoreward. The breaking does not belong to one instant. It stretches into a zone. Water falls. Air is trapped and shredded into countless bubbles. White water spreads in a long, tumbling band. The sound here is not a single impact. It is a hiss that continues, a soft roughness laid over the shore. The image returns with each spilling line. A pale rim folding forward, then another, then another. Foam travels on. The wave does not seem to throw itself down so much as surrender in increments. Over a broad surf zone, energy is released gently and at length. The shoreline receives a long, foamy push. Sand is stirred and carried along. Fine grains remain in motion. The coast is adjusted by this repeated softness, by this persistence more than by force. Elsewhere, the bottom rises more quickly. The same adjustment is compressed into less distance. The steepening happens faster. The crest thickens. It gathers into a lip, and then it curls over in one heavier motion. For a brief moment, the lip throws forward and down, enclosing a pocket of air. The shape is clean, almost sculpted, and then it collapses. When that lip lands, the water bursts outward and downward in a compact strike. Air, water, and suspended sand are mixed together in a dense, bright confusion. The sound is deeper here, shorter. A thud, a crash, sometimes a boom. The force is concentrated into a narrow place. Repeated there, it can dig the beach face steeper or deepen a trough just offshore. And that changed bottom waits for later waves, ready to alter them in return. Longer period swell often carries this kind of crest more readily when the slope below is suitable. Its shape has time to build. Its top becomes thicker, more organized before it falls. Smaller, steeper wind waves often come apart sooner. They spill messily instead of curling cleanly. Yet even in one group of waves, this can change from crest to crest. A larger set wave may plunge where the smaller ones before it only spilled. Its greater height changes the balance. It reaches instability sooner. It asks more of the same depth. Sometimes a wave meets a bar offshore and breaks there first. A line of white water appears over the hidden rise. Then behind the bar, in slightly deeper water, the wave can gather itself again. It reforms. It comes on. Farther in, it may break a second time on the inner slope. Between bar and shore, there may be a trough, a brief deepening that delays the next collapse. The surface there can look almost composed again, though the earlier breaking still lingers in bubbles and turbulence beneath. Tide keeps moving through all of this without haste. Over a fixed sandbar, a rising tide can soften what was once a plunging break on the bar crest. The active break shifts shoreward. The same incoming wave may spill farther in instead. With falling tide, the bar becomes shallower again. Waves trip earlier. The break zone moves seaward. Familiar surf lines drift outward and inward over the course of hours, as if the whole shore were breathing. Where waves approach at an angle, one end of the crest enters shallow water first. The line of breaking peels along shore. It does not collapse everywhere together. Refraction bends the crest as different parts slow by different amounts. In some places, that bending gathers energy, focusing it on a headland or the crest of a bar. There the waves steepen sooner and break with more force. In other places, the energy is spread across a wider front. The same swell arrives more gently there, and the break happens farther in. So along one stretch of coast, neighboring waves can live very different brief lives. There are shores where dramatic plunging seldom arrives. In sheltered bays, smaller waves may never gather the needed steepness, even where the beach itself is relatively steep. The lines come in, rise a little, and subside into less emphatic forms. There are also coarse, pebbled beaches that hold a steeper face than fine sand often does. On such reflective slopes, waves may surge instead of curling. The nearshore water stays relatively deep until the last moment. Then the wave rushes up the beach face with little offshore tumbling foam. Much of the collapse is delayed until the water is already climbing the shore. The white water is less spread out. The momentum is spent on the steep face itself. Surging has its own quiet severity. There is less broad hissing, less of the long, airy unraveling seen in spilling surf. Water runs up and then runs back. On steep beaches of pebbles and coarse sand, swash and backwash move those heavier grains back and forth with little time spent suspended. The motion is direct. The beach face gleams, darkened and smoothed by each rush. After any break, whatever its style, the wave does not simply end. The collapse turns into turbulence, into bubbles, into a moving wall of foam that continues shoreward after the crest itself is gone. In very shallow water, it becomes a bore, low and white and persistent. The uprush begins at once, carrying water and sediment up the beach. Then backwash returns, meeting the next incoming wave. Sometimes that meeting softens the next break. Sometimes it sharpens it. The timing shifts from moment to moment, and the shore keeps answering. The water in the break zone is briefly changed by air. Bubbles make it lighter for a moment. Sand grains and foam move differently there. Fine sediment lifts and drifts. Coarser grains settle sooner. Along gentler coasts, spilling surf can keep more suspended sand moving quietly along shore, redistributing it from one reach of beach to another. In places of repeated plunging, bars and troughs can be carved and remade, and these shapes then guide later waves toward new lines of collapse. Near inlets or river mouths, channels and shoals shift from week to week, and familiar surf may begin toppling in a new place without ceremony. So the shore is never fixed in just one expression. A coast can flatten under one season of waves and steepen under another. Broad, foamy surf can spread across a long zone for days, carrying its hissing sound over the shallows. Then a storm swell may arrive taller and longer, and the balance changes. The break grows heavier, the impact narrows, the sound deepens. Sand is lifted, dropped, pulled, and placed again. The beach remembers each pattern for a while, and then forgets it under the next. By the end, what remains is not a single moment of breaking, but a repeating arrangement. Swell arriving from deeper water, hidden bottom rising to meet it, the crest leaning forward, the white edge appearing, the shore receiving what comes. The details shift with tide, with bars, with angle, with the larger and smaller waves in each uneven group. Yet the scene returns again and again. A line forms, a line steepens, a line falls. Sometimes it falls gently in a long hiss of bubbles across a broad pale band. Sometimes it folds into a thicker lip and lands with a shorter, heavier sound. Sometimes it hardly breaks at all until the last instant, when the water runs straight up the steep face of the beach. Each form belongs to the same meeting of height and wavelength and slope and depth, though no single number holds the whole decision. The shore keeps that decision in motion. The sea keeps asking it again. And long after any one crest has collapsed, the pattern endures. Offshore bars wait below the surface like quiet steps. Tides rise and lower over them. Sand shifts, settles, and is lifted again. New wave groups arrive with their uneven ranks of smaller and larger lines. In the dim, steady work of water over ground, the place of breaking moves a little seaward, a little landward, and then returns. The white edge forms, foam spreads. The rush climbs the shore and slips back. This remains night after night, long after the individual wave is gone.